All right, in this podcast, we are going to get further into rate laws. We're going to actually look at what's called the differential rate law. There are steps to determining the differential rate law. You have a differential rate law situation when the data you're given is rate and concentration. So you're actually told the rate and you're told the concentration of the reactants, okay? So this is going to be a situation where you need to use the differential rate law. I don't really like steps, but I made steps for you just in case it was helpful for you. So if this is helpful, that's great. You can pause it and copy these steps down. Okie dokie. So I'm more of a visual person. I like to see it done. All right, so basically we are trying to write the rate law and determine the value of the rate constant and then the overall order of our reaction. Okay, so first off, I just like to go ahead and get like a generic rate law written. It just helps me out to know what my aim is. So rate equals K, right? And then it's going to be to these two, right? And we got concentration, so I get to use my brackets. And CL2. All right, so what I'm looking for is I'm looking for the X and Y, or what's located up here on this, okay? So what have I got going on in terms of my order? How does this particular reactant's concentration affect my rate? Okay, all right, so we're going to go down here. I want to look at NO first. So if I'm going to change NO, CL2 needs to be remaining the same. So CL2 is remaining the same. Oh, well, looks like in the first and the second and the third and the fourth. So just pick one. All right, so I'll go with the first and the second. So this is staying the same. Okay, NO is doubling, right? So, okay, so if NO is doubling, okay, all right. And we go look at our rate over here, okay, and it looks like our rate went up by, anybody? Looks like a factor of 4 to me. Okay, so if I kind of like look at this in terms of the equation, right? So my concentration doubled, right? And my rate quadrupled. And remember, again, I'm looking for that exponent. So 2 raised to what would get me 4? Hopefully you said 2. So that means that it's second order with respect to NO. Okay? All right, now we want to look at CL2 now. So to look at CL2, you've got to hold NO the same. Okay, so looking at this data, hopefully you see that 1 and 3 are being held the same and the 2 and 4 are held the same. So I can do either. I'm going to go with 1 and 3. So looking over at CL2 now, we see that from 1 to 3, CL doubled, right? Okay, so I'm going to go over here. All right, so my CL doubled, right? Like that's what's in my brackets. Okay, and then my rate went from this to this. That looks like it doubled to me. Okay, so my rate doubled, my concentration doubled. What exponent has to be up there for my concentration to do the exact same thing? I mean, my rate to do the exact same thing as my concentration. Hopefully you said a 1. So you can write the 1 up there, or you can leave it and it's just understood to be a 1. Okay? All right, so that's how you determine a rate law. Okay, so this is the rate law right here. Okay, that's the rate law. Rate equal K, NO to the 2, CL2. Okay, so now that we've got the rate law, so check, got the rate law. All right, now we wanted to determine the value of our rate constant K. So I'm trying to find K. So in order to be able to find K, I have to know all this other information, right? Well, guess what? You know all of that information down here, and you already found your orders, so you're ready to plug in. So you just pick one equation, and you want to plug it in and algebraically solve for K. I like to go for the first one just because it's natural. So I'm going to go straight to number 1. Okie dokie. So I removed the rest of the table so I'd have a little room to write here. Okay. So I'm going to do experiment 1. Okay. So I know my rate. That's the first thing. So 1.43 times 10 to the negative second is equal to, okay, K is what I'm looking for. And then NO is 0.25, and that one's squared. And then CL2 is 0.25. Okay, and I'm going to solve for K using a little bit of algebra. All right, so we got a 0.25 squared times 0.25, so that's 0.25 cubed. So I got 0.015625, and that is still being multiplied to K, right? Oops, that's K. All right, and then I still got my 1.43 times 10 to the negative 6 over here. I'm going to divide to get my 0.015625 on this side. And then it'll cancel over here. Okay, and that gives me my rate constant as, all right, and a little calculator. I got 9.15 times 10 to the negative 5th. All right, so that's our value. Now, anytime you are asked for the rate constant, they're going to always go specifically they're going to say with units. And to get credit, you have to have the correct units. Okie dokie. Got that pretty much cleaned up there for us. Okay, so there are kind of 2 ways to look at how to approach doing the units for K. So the algebraic way to do it would be to plug all your units back into your equation and solve for the units for K, right? So over here, let's see, we've got rate. So rate is moles over liters. That's molarity. So I got molarity over seconds is equal to K. And then NO was molarity, and then that was squared. And then CL was molarity. So basically you've got K times meters cubed. Okay, now if you divide, I said meters, I meant molar, my bad. Okay, so if you divide to get K by itself, okay, well, it wouldn't let me write it down there. So K is equal to, so what do you do when you have a fraction, right? What do you do with that? So hopefully you were going to say that you flip it and multiply by the reciprocal, right? So what that means is we got M over S, right? Whoop, why is my pen not working? There it goes. All right, M over S, and then that M cubed, we're going to do the reciprocal of M cubed, so that's 1 over M cubed. All right, so that basically gives us, so we got an M here and 3 there. So this one will cancel out, and this one will cancel one of them and become a 2. So we'll have 1 over molarity squared seconds. Okay, so that's your units for K. If that completely just blew your mind, okay, there's a trick. So the units for K are always going to be 1 over molarity, and molarity is raised to the overall order. So this is not going to look like a superscript, but it's supposed to be like an exponent, like a superscript. So overall order minus 1, and then that is multiplied times your time. Okay, so to review, 1 over molarity. Okay, so we have to know the overall order. So the overall order is you're just adding exponents here. So overall order is third order. So 3 minus 1 is 2. And then our time unit was seconds. So there's your trick if the trick works better for you. If not, you can straight solve it out, okay? Last slide is about overall order because we were asked to find the overall order. Again, overall order is just adding your orders for your reactants, adding those exponents. So this is a third order reaction.